Hey everybody, just wanted to spend a little bit of time talking about the Octet Rule. And this rule is one of the kind of governing principles that helps us determine Lewis dot symbols and Lewis dot structures. And what the Octet Rule basically says is that because of the electronic structure of an atom, elements typically want to have 8 valence electrons, either by getting rid of or gaining electrons by transferring them, okay, or by sharing them, okay. So this is shown pretty straightforwardly here if we look at a periodic table. Okay, on the periodic table, the elements here, lithium, for example, lithium has 1 valence electron. Okay, actually everything in group 1 has 1 valence electron. And these elements in group 1 are very, very reactive. And then here, the alkaline earth metals in group 2 are also reactive. There's 2 valence electrons. It's because those elements want to get to 8 electrons, and that to make them stable. Okay. Now when we go all the way over to the other side of the periodic table, we get to the noble gases. The noble gases have 8 valence electrons. Okay. Now, these noble gases, they are called noble because they don't interact with any elements. Now, lately we've been able to get xenon. We've been forcing xenon to do some reacting, but not really, okay, not much. And so these noble gases here can don't react at all. They are inert. They do not react, inert elements. And so that's because they have 8 valence electrons. It's a very stable electron configuration. So if you have lithium with 1 valence electron, how can it get, I won't use lithium as my example. Let's use sodium here, excuse me again. Sodium, how is it going to get 8 valence electrons? Well, it has 1, and so it can either gain 1, 2, 3, 4, 5, 6, 7 valence electrons, or what it can do is it can lose 1 to have a valence that's exactly like neon. And that's what it does. It's easier to lose 1 electron than it is to gain 7. And so if we look at rubidium, rubidium can either gain 1, and we kind of ignore these D blockers. So it can either gain 1, 2, 3, 4, 5, 6, 7, or it can lose 1. Is it easier to gain 7 or to lose 1? It's easier to lose 1 electron. And so everything in this group 1, the alkali metals, okay, everything in that group will always lose 1 electron. And that's because of the Octet Rule. Okay. Now, when we come over here to the kind of the non-metal side of the family, side of the periodic table, not side of the family, I guess. Okay. When we come over here, now we get to the side of the periodic table where the elements want to gain electrons to become stable. So nitrogen, for example. Nitrogen has 5 valence electrons. In order to get to 8 to look like neon, okay, it can gain 3, or it can lose 5 to get back to this noble gas. Okay, it's easier to gain 3 than it is to lose 5. Okay, and so this side of the periodic table, if we look at the stair step separates this from the metals, which always lose electrons, and the non-metals, which always gain electrons. Okay, and the Octet Rule kind of exemplifies what's going on there, because 8 is the key number. So when we come back here, let's show what actually is going on here. Okay, so if we look at sodium, sodium if we draw the Lewis symbol of sodium, sodium has 1 valence electron. And chlorine, and we can see that if we look on the periodic table. Excuse me, I have there, better. Okay, so if we look at the periodic table, sodium has 1 valence electron. It's in group 1, it's 3s1 is the outermost valence here. And then chlorine is 3s2, 3p5, so it has 7 valence electrons. Okay, that's kind of the cool part about looking up stuff. So 1, 2, 3, 4, 5, 6, 7. Okay, so what do we notice? Sodium wants to give up 1 electron to have a valence of 8, the previous noble gas, which is neon, and chlorine wants to gain 1 electron. So what happens is this electron here gets transferred from here to here, and now we end up having stable ions or stable atoms, okay? Because this guy now is sodium, but it's lost an electron, so it's sodium plus, and then chlorine has 1, 2, let me make that a little bigger, 3, 4, 5, 6, 7, and then has a little, has sodium's electron, so it has 8, so it's gained an electron, so it's minus. And so now we've made an ionic bond. And so then I say, why do you think a reaction between these two things is so vigorous? Well, it's so vigorous because sodium really wants to give up that 1 electron. Okay, that 1 electron that sodium has really wants to be gone. And chlorine really wants to have it. So it's like 2 hyperactive elements getting together and just so excited that they have a really vigorous reaction. That is how the octet rule can help us in determining things about determining charges and Lewis symbols and things like that of metals and nonmetals. Okay, and that's what we are talking about here. Now, so here's the reaction. Okay, sodium plus chlorine gives us sodium chloride. Now, Na plus is an ion with a Lewis symbol, so it's Lewis symbol, Na, with a plus here. Now, anytime we have a symbol, a Lewis symbol, we always put in brackets. Okay, I'm sorry, not a Lewis symbol. Any ion that's a Lewis symbol, we put in brackets. That way, even though there's 0 electrons around it, we know that we have determined its symbol and it has no electrons around it. Okay, so the symbol for chlorine, 1, 2, 3, 4, 5, 6, 7, 8, we put brackets around it because it's an ion, and then we put a negative charge. Okay. Now, we can omit them here if we want to, okay? But I try not to because this tells me that we've determined that there is a Lewis symbol and that Lewis symbol has no electrons around it, okay? So, now we can figure out what the Lewis symbol is for the magnesium ion. Remember, we're trying to get to the octet rule. So magnesium has 2 electrons, and so we put it in brackets, okay, and then we go 2 plus. Okay, well, how did I get that? Well, we started here, Mg, with 2 valence electrons, okay, and again, we can tell that from the periodic table. It's in group 2 here, so anything in group 2 has 2 valence electrons. Okay, so it now wants to have 8 around it, so it loses its 2 electrons as opposed to gaining 6 more. Okay, now the oxide ion. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. So what's easier to get to the octet? Lose 6 or gain 2? Well, in this case, it's easier to gain 2. So 1, 2, 3, 4, 5, 6, 7, 8. and we put 2 minus because it's gained 2 electrons on the outside, 2 electrons, and by gaining electrons it becomes a negative charge. Now the arsenide ion, arsenic is As, okay, and it has 3 valence it has 5 valence electrons. So if we look at this, 1, 2, 3, 4, 5, it's easier to fill this to get up to 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And so now that becomes a 3 minus. Now aluminum has 3 electrons. Okay. So aluminum has 3 electrons. 1, 2, 3. Is it easier to gain 5 or lose 3? Well, in this case, it's easier to lose those 3. Okay. Maybe it lost them to arsenic there. Okay, and it became the arsenide. Maybe arsenide took these 3 electrons and gained them here. I don't know. Who knows? But whatever, aluminum is a 3 plus charge, and that's always what the charge is going to be. Okay. So there's only one exception to the octet rule, and that has to do with hydrogen and helium. Okay. The octet rule just means that we have a full S's and P's. Okay. Remember, the S's have 2 electrons and the P's have 6 electrons, and so 2 plus 6 is 8. That's where we get the octet from. But hydrogen and helium are an exception because they are up here, and so we end up having only S's, so a full S and P, well, there's no P's for hydrogen and helium, so it's just a full S. So here, helium will follow the octet rule, but it's kind of modified. It's actually a duet. Okay, it only has 2 electrons, and hydrogen follows that rule too. It only wants 2 or 0, because look at what can happen. Hydrogen, okay, hydrogen can, let's see, if it just wants 2 or 0, it can either lose 1 or gain 1 just as easily. Helium already has a full S, so helium looks like this, and we pair them because there's only S's. Okay, so that's your exception to the octet rule. Okay, so that describes the octet rule and how we use that in order to determine charges and Lewis symbols. Okay, for atoms and ions. So I hope that helps out.